Okay, this is the second part or large topic in chapter 19. Hopefully you've already learned kinetics, and now we're going to look at equilibrium. I like that I misspelled it before, but that's alright. So 19.2 is about reversible reactions in equilibrium. So a reversible reaction, which is a lot of reactions, for instance, water, liquid, turns into gaseous water, but gaseous water also goes back to liquid water. So this double-sided arrow means it's reversible. Equilibrium means at some point the amount of reactants and products will not change. So it'll reach a point where if you look at how much gaseous water is in a closed container, it'll be the same because there's a lid on it, no matter if you look now or in 2 days. Dynamic equilibrium means the reaction is still occurring in both ways. There might be 2 R's in occurring in both directions. So it's dynamic in that as one liquid turns into gas, and it's at equilibrium because if one goes this way, then one goes this way. So the overall amount doesn't change, but the reaction is still happening if you could actually see molecules with like special glasses or something. So that's what this section is about. In order to get started, we have to do a little bit of theory. And this is going to be 19.2. So equilibrium expressions. You're going to be writing an expression, and we'll use K, or they could use, so we'll use K, and K is going to be the concentration of reactants, concentration of products raised to the coefficient power over the concentration of reactants raised to the coefficient power, and since there are 2 reactants, we will multiply them, and that's what K equals. So it's products over reactants raised to the coefficient power. If there's more than one on either side, we multiply them. Let's try another one. Sometimes they call it K, sometimes they call it KC, sometimes they call it KEQ. I don't really care. It's K. So on this one, I'm going to do products over reactants raised to the coefficient power. However, liquids and liquids and solids are not included. And you should want to know why. Well, concentration is moles per liter. And you can't really have a concentration of a solid or a concentration of a liquid. They're pure. The concentration's infinite. So those make no sense in there. If the at confuses you, just don't put them in there. No big deal. So products raised to the coefficient power over reactants raised to the coefficient power. And I just pretend bromine's not there. Let's try another one. Okay. Products raised to the coefficient power over reactants, but wait, it's a solid, so I can leave it like that. If you want to put a bar and put a 1, you can, but it doesn't matter. So what does K mean? If K is greater than 1, you will have mostly products. Or how about more products? Let's put more products at equilibrium. If K is less than 1, you'll have more reactants at equilibrium. If K equals 1, for this book, we're going to say products equal reactants. This is really rare. So K is greater than 1, K is less than 1 is the normal case. Let's put some numbers to this. Now, this is for sure an honor standard. In CP, it's going to depend on your teacher and the year and the speed we're going that year. So here it goes. Example 4. Analysis of the equilibrium mixture in a 1 liter flask at 300 degrees, honestly, who cares, gives the following results. So I have that many moles. I want to calculate KEQ. So I'm going to write a generic K equation. So KEQ is products to the coefficient power over reactants to the coefficient power. I have more than one reactant, so I will multiply them. And that should work. Now let's try and plug stuff in. The brackets mean molarity, which equals moles per liter. So I need to change all this. So 0.15 moles divided by 1 liter is 0.15 molarity. And 0.25 molarity. Same thing. They're all divided by 1. Always check though. Could have been different. So now I'm going to just take these numbers and put them in here. So NH3, 0.10 squared. N2 is 0.25 to the first. And H2 is 0.15 to the third. And then it's calculator time. 0.1 times 0.1 divided by 0.25 divided by 0.15 raised to the third. I get 11, I'm going to use sig figs, so I get 11.85. I'm going to clean that up to 12. And we're going to leave this as a unitless number. Your book puts units. College and the AP does not. So once again, if you're in CP, follow your teacher's lead. So 12. Since K is greater than 1, there will be more products. So if I were to look at this, I would expect to see more ammonia than those two. That's the point of this. Now let's look at the next one. This one says, based on number 4 above, calculate KQ for this. So let's look. I'm looking at the equations, and it looks like they are flipped. So the products became the reactants, and the reactants became the products. The products became the reactants, and the reactants became the products. So instead of being 12, it's going to be 1/12. And just because we like numbers, not fractions, I'm going to change that to 0.083. So really it was just a flipping. You could have calculated it out, and if you want to, go ahead. This is the more savvy way to do it. Example 6. We're just going to try a couple different examples and make sure life works out. Suppose you have this following equation, and you have a mixture in a 1.5 liter flask. You have half a mole of nitrogen and oxygen and 0.2 moles of nitrogen monoxide. Calculate K. So I'm first going to do the generic. KQ equals products raised to the coefficient power divided by reactants raised to the coefficient power. And I should make note, I do quickly check for solids and liquids. There's none. Now I'm going to plug stuff in. The brackets mean molarity, so I need to change the moles to molarity. So I need to take 0.5 and divide it by 1.5, because that's moles divided by liters. So let me calculate that for you. 0.5 divided by 1.5, 0.33 molarity. This is the same calculation, so 0.33 molarity. And this is 0.2 divided by 1.5 is 0.13 molarity. Now I can plug in my numbers. Nitrogen monoxide's on the top, so 0.13 squared. Nitrogen's in the denominator, 0.33 to the first, times the oxygen, which is also 0.33 to the first. Calculator time. Two sig figs, so I got 0.1551 blah, blah, blah. I'm going to clean it up to 0.16, unitless. So in this case, K is less than 1, so reactants are favored. So at equilibrium, I'd expect to find more reactants than products, which is interesting if you were trying to make products. This is a bad reaction, not really good, or a lot of patience is needed. Let's try another couple. This one, I'm going to add 0.53 moles of hydrogen and 0.053 moles of carbon dioxide, and they're put in a 1 liter container. And then I have a K, so I want to know how much I have at equilibrium of carbon monoxide. So I'm going to set up what we like to call a rice chart. I'm going to do a quick check for any liquids and solids, none. Rice chart, the reaction, the initial concentrations, the change in concentrations, and the equilibrium concentrations. I'm going to fill in what I know. The initial concentration of hydrogen was 0.053 divided by 1, which is 0.053 molarity. The initial concentration of carbon dioxide was 0.053 divided by 1, which is 0.053 molarity. It doesn't say that I put in any water or any carbon monoxide, so it's 0. If they don't say anything, assume they didn't put it in there. And I know K is going to equal 0.786. So let's start with the generic. So sometimes you just need to have confidence and scooch on. So the generic is K equals products raised to the coefficient power times the other product, whoops, I miswrote, but you'll be fine, to the other coefficient power, that's carbon monoxide, divided by reactants raised to the coefficient power times the other reactant raised to the coefficient power. I'm going to plug in what I know. At equilibrium, I know 0.786, the K equals, I don't know how much I made. So in algebra, when you don't know, you just put X. And here, if I started with 0 and I ended with X, I must have made X amount. And if I made 1 water, I must have had 1x of those go away and 1x of those go away. So 0.053 minus x. I started with that and I lost that. 0.053 minus x. I started with that and that went away. So the equilibrium concentrations are what I use for K. Not initial, not change. Equilibrium goes with the equilibrium constant. So K equals x raised to the first times x, right there, raised to the first, divided by, the hydrogen is 0.053 minus x raised to the first, times carbon dioxide is 0.053 minus x raised to the first. Whew, big bar. And now it looks like a lot. I'm going to change this x into a multiplied dot because I can't have so many X's. It makes me nervous. Now we're going to use algebra, so I'm pull out algebra pen and see what we can do. All the way over here. 786. I'm just cleaning life up here. 0.053 minus x squared. I'm going to square root both sides. So let's see what I get here. So I need 0.786. I need to take the square root of it. I also need to learn how to use my calculator, so I'll go the other way. 0.786 is 0.887. So 0.887 equals x over 0.053 minus x. I'm going to do a little cross multiplying. So 0.887 times 0.053 is 0.0470, that times that, minus 0.887x, cross multiplying, x times 1 is x. I'm going to collect like terms, so 0.0470. I'm going to add 0.887x to both sides. So I'll get me 1.887x on the right. I'm going to divide both sides by 1.887. So 0.0470 divided by 1.887 equals 0.0249. And it asks, what was the equilibrium concentration of carbon monoxide? X. So there's his concentration. If you're still with me, we should look at sig figs. 2 sig figs, 2 sig figs, 2 sig figs. So I'm going to let that equal 0.025 molarity. At this point, I wouldn't stress too much about sig figs. You can lose a point, but did you understand all of that? Okay, let's try another problem. This will be our last big equilibrium problem. So, if you put some HI, reacts, produces an equilibrium mixture of 0.5 of both products, and you're given the K, calculate the equilibrium concentration of both products given this K. So, I'm going to write a generic K. K equals products raised to the coefficient power over reactants raised to the coefficient power. I'm going to rice chart it. You don't have to, I just like to. R for reaction, I for initial. If some HI, okay, so I don't know how much sum is. So sum, maybe we'll come back to that, produces an equilibrium, so the E, mixture 0.5H2, 0.50 molarity H2. Calculate HI, this is my goal, and I, so that's my goal. It doesn't say I put any of those in there, so those are zeros. If I started with no H and I ended up with 0.5, I must have gone up 0.5. That was my missing number. So this plus this equals that. That has to be the number. Look at the balanced equation. If one of these is produced because of the coefficient 1, then one of these is produced. So I start with 0 and I'm going to go up 0.5. 0 plus 0.5 is 0.5. I've answered one of my questions already, but I'm not done. So K, I'm going to plug in here, is 0.020. I'm just plugging these numbers. Remember, equilibrium goes with the equilibrium constant. So hydrogen is 0.50 molarity raised to the first. Iodine is 0.5 molarity raised to the first. I don't know what that is. So I'm just going to put it in there. I don't know. I know it's squared because of that. So now I'm just going to play some algebra. Pull out my algebra color, red, because algebra causes stress for some people. I think I'm going to just do a cross multiplies, and you can watch me do that over here. 0.2 times that, 0.02 rather, times